Hello everyone. In this video, I am explaining why modulus function is not differentiable at x equal to 0. First, let us see the graph of modulus function. This is the graph of modulus function. At x equal to 0, we have to show that it is not differentiable. We know the fact that geometrical meaning of derivative is slope of the tangent. Derivative at any point x equal to a is slope of the tangent at that point x equal to a. Now look at the point x equal to 0. As soon as you look at the graph of this function at x equal to 0, x-axis looks like a tangent to the graph of the function. So if x-axis is the tangent, slope of x-axis is 0. Therefore, the derivative of this modulus function at x equal to 0 must be equal to 0, isn't it? But that is not happening here, because at x equal to 0 there is a sharp change or sudden change in the graph of the function. There is a sharp peak here. So due to which, though x-axis looks like a tangent to the curve at x equal to 0, this tangent is not stable. It doesn't reside at the point x equal to 0. It fluctuates. It toggles, or this tangent or this x-axis dances at this point. You don't get a particular value for the slope at x equal to 0. It toggles between negative and positive, negative, positive. So because of which we can't define a specific value for the slope. Hence we say that the modulus function is not differentiable at x equal to 0. That is how to understand it geometrically. Now, to prove the same thing algebraically, we have to prove that LF dash of 0 means left hand derivative of this function at x equal to 0 is not equal to right hand derivative of this function at x equal to 0. So we know that the modulus function definition as x greater than or equal to 0, it is minus x when x is less than 0. So as per this definition of the function, we know LF dash of 0 is given by limit h tends to 0 f of 0 minus h minus f of 0 divided by minus h, where h is a positive change, that is where h is positive, very small quantity. And this is the definition of left hand derivative. I know now why the modulus function is not differentiable at x equal to 0, because it has a sudden change or this sharp edge at x equal to 0, due to which the tangent is not having the stable value, it is having the fluctuating value. See, when you have a switch, either it is on or it is off. If it is in between, you can't determine the state of that switch, correct? No, either it is on or it is off. Same thing here. Though x-axis looks like a tangent line, but this line is fluctuating. It dances. This tangent dances at the point x equal to 0, due to which you are not getting a particular value for slope. The same I have to prove here algebraically. That is what I am doing here. The left hand derivative I am calculating, which is equal to limit h tends to 0 f of minus h minus f of 0 divided by minus h. This is the definition of left hand derivative. Now substitute this in the function h tends to 0 f of minus h. What is f of minus h? H is minus h means it is negative, so you have to choose this value minus of minus h, which is positive. Limit h tends to 0 h minus f of 0. Put x equal to 0 in this function, it gives you 0 divided by minus h. So this gives you minus 1. So left hand derivative is minus 1. That means as x approaches 0 from the left side, the derivative is minus 1. Similarly, let us find out the right hand derivative. Rf dash of 0 equal to limit h tends to 0 f of 0 plus h because it is from the right side, minus f of 0 divided by plus h. This is equal to limit h tends to 0 f of 0 plus h means f of h. F of h is, what is the value of f of h? It is h, because h is positive. So this is equal to h minus f of 0 is 0 divided by h cancels, this gives you 1. Therefore, right hand derivative at x equal to 0 equal to 1. Means as you approach the point 0 from the right side, derivative is 1. So we don't have the common value for left hand and right hand derivative. Therefore, we can conclude that f is not differentiable at x equal to 0. That means modulus function is not differentiable at x equal to 0, but this modulus function has derivative at points other than 0. Okay, for x less than 0, its derivative is minus 1. For x greater than 0, its derivative is 1. We can't conclude that the modulus function is not differentiable anywhere. That is wrong. Modulus function is not differentiable only at x equal to 0 because it is having the kink or the sharpness at x equal to 0. At all other regions, the function is behaving normal. Okay, so when x is less than 0, the derivative of modulus function is minus 1. When x is greater than 0, the derivative of modulus function is plus 1. And at x equal to 0, the function is not differentiable. This is how we explained it both geometrically and algebraically. To prove algebraically, we have to show left hand derivative equal to right hand derivative. That is not happening at the point x equal to 0. Hence, the function is not differentiable at x equal to 0. I hope you understood the concept. Thank you for watching.